So I promised that today we talk about the computing. So we build a model how to generate languages or how languages evolves in time yesterday. And today we want to do the computations to find our posterior. But before I get into that, I just wanted to talk a little bit about the clustering in the end of yesterday. So we had a Markov chain between sound segments, and there was a discussion about why was I throwing away information about directionality when I did the clustering. So the way I was thinking about the clustering is that I get each sound segment and believe that and pretend that it's a weight, and then I put it somewhere in a two-dimensional space. And then clustering is just grouping these weights into an equivalence class, such that inside the equivalence class, it's easy to move one way to another, and outside the equivalence class, it's hard to move one way to another. That's how I was thinking about clustering. And since it's an equivalence class, I cannot, it has to be equally difficult to move weight 1 to weight 2 or weight 2 to weight 1 or something like that. So maybe and clustering was just a way to summarize information and get some type of qualitative ideas about the sound segments and compare them to what linguists knew. So in the end, we compared the sound segments to the classes, the qualitative classes that were defined by linguists, and they were equivalence classes, right? But perhaps that's not the best way of summarizing the information that we have, the phonetical information that we have about sound segments. But then I don't know exactly what I would do. Well, the analogy that I would think is that perhaps some of these, this is perhaps not a plain field. Some of these sound segments are on the top of the hill. Some of them are in valleys. And then it's not equally easy to move A to B than it is to move B to A, and then try to summarize this. But I didn't think about how to do that, just an open idea. And maybe then I could use, instead of the similarity measure that treats sigma 1, if sigma 1 is similar to sigma 2, then sigma 2 is similar to sigma 1. Instead of doing that, maybe then I could use a non-symmetrical similarity measure. But just something that I was thinking about based on yesterday's questions. But that said, I'd like to move to the part how to compute the posterior, so the computational ideas. And in the end, what I applied is some type of version of what's called nested sequential Monte Carlo. And I didn't want to talk a lot about the exact algorithm that I used in the spirit that this is a tutorial, but how to get there. So the algorithm is nothing less, it's nothing more than just applying a sequence of tricks that are seen in, that you can find in the literature. So I'll try to summarize all the literature that you have until you get to the nested sequential Monte Carlo. And I'll summarize it by presenting the tricks that, okay, this is just applying this. And I promise that the tricks are very simple. So in a sense, in order to get to nested sequential Monte Carlo, it's all based on the theory of sequential Monte Carlo. And the way to think about this, it's very different from, at least I say, it's very different from Markov chain Monte Carlo, in which you imagine that you have a very long chain, and after you run it for a long time, you're close to the posterior distribution. The idea of sequential Monte Carlo is closer to importance sampling, in which you imagine that you have several particles, so you don't have a chain running for a long time, you just have several particles that you sampled, and then you have a particle weight attached to all of them, and then in a sense you're taking an average of these particles. So I find it easier if you want to think about sequential Monte Carlo. The prototype is importance sampling and not Markov chain Monte Carlo. That's the way I see it, at least. So I'll just discuss, just in the spirit of the tutorial, very quickly importance sampling, because I believe most of you know it. The idea of importance sampling is that you want to sample from some random variable theta that has this density f of theta, but it might be hard to sample directly from f of theta. And in particular, you want to compute the expected value of a given function of theta, let's say. Right? With this, you can find what the density is if you can compute this for every h, in particular, right? So the idea is, instead of generating a random sample from f of theta, you generate a random sample, epsilon 1, epsilon n, IID, from another distribution, f of epsilon, which is usually simpler than f of theta. You can sample from it in some way. And then you don't know how to compute f of theta, but you know how to compute it up to a constant of proportionality. And you might not know how to compute f of epsilon, but you know how to compute it up to a constant of proportionality, f of epsilon tilde here. So tilde, in this tutorial, I'll always use tilde on top of it, meaning that it's not a density up to a constant of proportionality. And then, can you use epsilons to somehow estimate or approximate the expected value of h of theta? And then importance sampling just tells you that if you define the importance weights as how far apart this epsilon that it was simulated is from f of theta, so just a ratio of f of theta and f of epsilon, so to each particle you attach this weight w, and then you just compute the average of h of epsilon, but average over these particle weights, then you know that if you take the number of particles going to infinity, then from the law of large numbers, you are just approximating this quantity that you wanted to estimate, so the expected value of h of theta. And then there's a question about, okay, so what's the best distribution that I should sample the epsilons from? And then the answer is tautological. If you want to reduce the variance of your estimate, then the best proposal is, of course, f of theta, in which all the sample weights are equal to 1. And that's not very fulfilling because, of course, you cannot do that. But then, so the heuristic here is that you want these sample weights to be approximately uniform. If they're approximately uniform, then your sample size is going to be large. Where the sample size is more or less measured by the variance of the weights. So that's just importance sampling, and it will be used to define this generalization, which is sequential importance resampling. But before we get to that, I'll just rephrase importance sampling in another way that makes it easier to build the analogy. So there's this other idea that is sequential importance sampling. And it's just a particular case of importance sampling. So the difference is that here theta is a vector in RD, and it has this density f of theta. And we have the exact same problem. And we generate these proposals from a joint distribution f of epsilon. And we want to estimate E of the expected value of h of theta. So in principle, we could just do importance sampling again. The weight of each one of these particles is just the joint density of theta divided by the joint density of epsilon. But we can decompose these weights according to the conditional. So the density can be decomposed into the, let's say, f of theta 1 times f of theta 2 given theta 1, and so forth. And we can just decompose the density of f of theta and the density of f of epsilon into their marginals. And then, therefore, we can write W as the product of the weights in each one of the dimensions that we are decomposing. That is just the conditional distribution of theta I given all of the paths of theta over the conditional of epsilon I over all of the paths for epsilon. So what's important here is this idea that you can decompose the weight into conditional weights. The weight that is given to a vector is just a product of all of the conditional weights. And this weight here, or actually this product of conditional weights, is going to appear in the framework of sequential importance resampling. So this is just the algorithm for sequential importance sampling. I'll just skip this. And then, so we are building towards this idea of sequential importance resampling. And the idea is that, let's say that you're simulating, you're doing the idea of sequential importance sampling, in which you are generating one coordinate of epsilon at a time. And you can compute your conditional weights at each coordinate that you're generating at a time. And you can look at the partial calculation for the weight. Let's say you generated, the random vector has d coordinates, and you generated the vector until coordinate j. So you have the product of the partial weights until coordinate j. And then you can look at the weights until coordinate j. And let's say you look at these weights and you find that some of these weights are really high and some of these weights are really low. So once you do the final calculations, when you simulate it from all of the coordinates, you already know that since these weights until state j are really low, really close to 0, it doesn't really matter what you simulate in the future. The combined weight is going to still be really low. So in the end, when you're taking this weighted average, it won't matter. This particle won't matter at all. So why don't you just save the trouble and just eliminate this particle? That's more or less the idea of sequential importance resampling, right? But how do you eliminate this particle and at the same time keep the consistency results that you want? So that's what sequential importance resampling will do for us. So we just define this quantity, the product of the weights, in the same way that we had in sequential importance sampling. But now we can think these weights as being arbitrary. We just need that the product of them satisfies the same combined weight as we had in sequential importance sampling. And then sequential importance resampling works like this. We generate the first coordinate from the proposal. So let's say epsilon tilde 1, 1, epsilon tilde 1n, where n is the total number of particles. And they're generated just according to the first coordinate for epsilon. And then we just take the actual epsilons that we're going to use in sequential importance resampling as a weighted sample from these epsilons, but a weighted sample that is weighted by their marginal weights, right? And it's a weighted sample, of course, without replacement, because if it was with replacement, we just get the same sample again. But once we take this weighted sample without replacement, then what's going to happen is that the particles that have very little weight are not going to be resampled, so they just die out. And the particles that have a large weight, they will be resampled several times. So they are promising. We'll look further into them. And then we just repeat this process for all of the coordinates from 2 to d. So we generate the epsilons from their conditional distributions, and then we take the weighted sample of these particles using their marginal weights. So that's the idea of sequential importance resampling. That's how it works. And the result that we have about it is that if all the marginal weights are bounded and they follow the equation that we had for sequential importance sampling, so the product of these weights is exactly the product of the conditional distributions that we want to sample from over the conditional distributions that we're actually simulating from. Then if we take the average of H computed over where we simulated from, it's going to be exactly the expectation that we want to approximate. So in a sense, these epsilons that we are simulating from after we do sequential importance resampling are being approximately sampled from the posterior or the distribution that we want to sample from. And if you wanted to summarize what's going on, it's just that we do in each coordinate, we do importance sampling, and then we get the weights. And then we just bootstrap according to these weights. And then we get our actual sample. And then we just go to the next coordinate and simulate from the conditionals. We get new weights, we bootstrap from the weights, and so on. And in the end, we have lots of coordinates, lots of particles, and they are approximately being simulated from the joint density that we want to simulate from. This is a simplification of the full generality of sequential importance resampling. That I'm saying that you are resampling in every coordinate, but you don't have to do that. In some coordinates, you can just keep the weights as they are. And then instead of, so for example, when would you do that? When all the weights are approximately the same. Let's say if all of the weights are 1, then all of the particles seem promising. So you don't feel like you have to add more noise to the estimate by resampling. The idea of resampling is just throwing away some of the particles. So some generalizations of sequential importance resampling allow you to only resample when some of the particles or most of the particles look unpromising. And then you do the bootstrap. So then you have to do some adaptations. But this is just a simplification so that we can get the idea. So sequential importance resampling is more or less the same as sequential importance sampling, but in such a way that we do bootstrap for every coordinate, between the iterations for every one of the coordinates that we are sampling from. And as a result, when we want to estimate the expected value of h, instead of taking a weighted average, we are just taking the simple average of the epsilons. That's why they are approximately simulated. Once we bootstrap, they are being approximately simulated from the density that we want to approximate. So that's sequential importance resampling. And this theorem here that I presented is more or less the only theorem that we need. The idea is that sequential importance resampling is a very generic scheme, a very abstract scheme. And then we will try to fit the theorem for sequential importance resampling into the type of problem that we have. So there are successful uses of sequential importance resampling in different contexts, and they are built one as a function of the other. So that's the only theorem that we'll use. But then I'll present some ways of deciding how to build your sequential importance resampler. And the different tools that we'll study, or that I'll go over, are sequential Monte Carlo. So that's the most basic one. Then there's advanced, a particular case of sequential Monte Carlo, which is poset sequential Monte Carlo. So sequential Monte Carlo is usually thought of as this sequential importance resampling for vectors of numbers. The poset sequential Monte Carlo, then instead of thinking about as a vector of numbers, instead of that you have a combinatorial object of some type. So you want to sample somehow over trees, let's say, or over graphs. And then you have to think about these trees or graphs as sequences of vectors so that you can put them, vectors, so that you can put them in the framework of sequential importance resampling. And then once that's done, then I'll discuss nested sampling. So remember that our parameter space was something like, I can go back to that. Our parameter space, it had two types of parameters. First of all, we had a tree, so that seems to fit well with poset sequential Monte Carlo. And then in each node of the tree, we had extra parameters, which are the regular changes that happened from one node of the tree to the other. So then it will become very difficult for you to imagine, or at least for me, it was difficult to imagine topology in this joint parameter space in which you have not only the tree, but attached to each node of the tree, these vectors of regular sound changes. So the idea here is that we'll try to put one sequential Monte Carlo for the regular sound changes inside of another sequential Monte Carlo for the evolution of the tree in order to get the posterior. And that's what nesting is doing for us. So we have a parameter space that is more or less something times another thing. Let's say it's 3 times regular sound changes. And it's hard to think about a topology or proposals in this joint space. So somehow we break the problem into thinking about just trees on one side and just regular sound changes on the other. And we do that by nesting the samplers. And why does that work? Well, I'll discuss this in a couple of slides. Okay, so the idea that we have here is if we are following the sequential importance sampling scheme, in which we are proposing from each one of the coordinates at a time, and then we are computing the sample weights for these coordinates, and then bootstrapping to get approximately from the density that we are interested in. Then we can get a sample that comes approximately from the posterior and compute the quantities that we are interested in. So how do I apply that if I don't have a vector, but I have a single distribution that is very complicated? And that's the idea of sequential Monte Carlo. So instead of sequential, the framework of sequential importance resampling, in which theta was a vector, here theta is just a real number, but it comes from a really complicated distribution. So can we use somehow sequential importance resampling for us to sample from this f of theta? And what's going on here? If we just try to, what does f of theta being really complicated mean? It means that if you just try to build a proposal for it, most of the sample weights are going to be very close to 0. So you would not like to do a single proposal. You'd like to refine your proposals in a certain way so that you got better weights, or weights that were closer to the uniform distribution. So can we somehow benefit from sequential importance resampling to sample from this complicated distribution? And the answer that I found was given by this paper from Moral from 2006, and it's where he defines sequential Monte Carlo. I think it's published in Bayesian analysis. And the idea that he has here is that instead of thinking of theta as a single real number, we are going to think about it now as a vector of real numbers. And this vector of real numbers is going to have this density here. So what does this density mean? It means that in the last coordinate, it has exactly the density that we're interested in. The last coordinate of our vector, right? So the last coordinate is precisely f of theta. And then you can think about this as a reversed Markov chain in which from the last coordinate, you're simulating to the previous ones. So here you have Markov transitions, but these Markov transitions, they go from the future to the past, right? So you get your last coordinate, and then you just iterate through this Markov chain back to the first coordinate. And this is the density that you want to simulate from, right? And then, of course, just by marginalizing out, you can prove that in the last coordinate, the marginal distribution is exactly the f of theta that you're interested in. So this is a trick to put the quantity that you are interested in into a random vector, and therefore it can be approached by sequential importance resampling. Right? So to see that the marginal has the appropriate distribution, the only thing that you have to do is sum over all the coordinates, and the sum will just enter this product here, and it will just sum to 1. So the last coordinate has exactly the distribution that we want to sample from. Okay, but how is this helpful? We wanted to simulate from f of theta. Instead of simulating from f of theta, we are going to simulate from something that looks even more complicated. Why would it help? That's a question that you might have. The idea is that you will try to, at each step, choose a distribution that is a little bit closer to f of theta that you're interested in. And then in the end, the sample weights are going to be close to each other. They're going to be uniform, and then you get a better estimate for the distribution that you're interested in. So here you have these arbitrary marginal distributions, f of theta I. And these are what you're thinking about as approximations for the complicated distribution that you're interested in, right? So you pick, let's say you pick as your first coordinate something that is very simple, let's say the uniform distribution. And then let's say for the second coordinate, you might pick something that is a little bit more complicated to simulate from. So I don't know, you might pick a beta. And then for the third coordinate, you might pick something that is a little bit more complicated. I don't know, the mixture of betas. And then you might be making the distribution a little bit more complicated as you go. And the idea is that if you get to the full, if you wanted to simulate precisely from f of theta, directly from f of theta, then it would be very complicated. It would be very hard to get some proposal that was very close to f of theta, and therefore making the weights approximately uniform. But if you do this sequentially, then it might be easier to make, it might be easy to make the ith coordinate to be close to the I-1 coordinate. And then you'd find a way to make these proposals to have weights that are approximately uniform. That's what's going on here, right? So you define the weight of a given coordinate as being just this marginal distribution of theta j, so the jth approximation of f of theta, multiplied by that Markov transition that we had in the previous slide, divided by the f of theta of the j-1 coordinate, and then multiplied by what you're actually sampling from. And what happens here, if you pick these wj's, then you have a telescopic product in which these arbitrary functions that are approximating theta, they cancel out, right? So for W1, you have W1, f of theta 1 in the denominator. For W2, f of theta 1 will appear in the numerator, and so on. So after you take the product of these weights, all of the thetas are going to cancel out. All of these arbitrary approximations that you're taking are going to cancel out. And the only thing that is going to remain is the last coordinate that you wanted, because it doesn't cancel out in the telescopic sum, multiplied by these tj's that you had for each one of the coordinates, and then divided by the multiplications of the distributions that you are actually proposing from. And this is precisely the weight that you'd have in sequential importance resampling if you had this as the distribution that you want to, your target distribution for your random vector, and this is where your proposals are actually coming from. So in the end, you changed the weights in such a way that each one of the weights is not the marginal weight for that coordinate, but the product of the weights gets you where you want to sample from. It gets as the numerator the target that you want to sample from. And that's the only thing that we required in sequential importance resampling, that the product of these weights is calibrated, that it follows this equation, this ratio here. And as a result, if we just follow sequential importance resampling using these partial weights, then in the end, the sample that we are going to get is going to be approximately equal to a sample that comes from this distribution. And therefore, the last coordinate of this sample has approximately the complicated distribution that we want to sample from. And as a result, what we get is that we can compute the estimates that we can approximate the estimates that we are interested in. And what's good about this is that these weights, we can expect them to be approximately uniform, because we have the jth order of approximation divided by the j-1 order of approximation for the distribution, and we choose these approximations to be successively better. And therefore, therefore we expect the weights to be approximately uniform. But the problem with sequential Monte Carlo, if you want to apply is the problem, or what's good about it, is that there are several degrees of freedom. So what are these approximating distributions that you're going to take? What are these epsilons that you're going to actually sample from? And what is this reverse Markov chain that you have access to? So it gives you lots of degrees of freedom, and that's good because you can apply it to many different problems, hopefully by choosing these degrees of freedom in a smart way. But we are interested in applying sequential Monte Carlo to trees. And one way of doing that is using Poset sequential Monte Carlo. So Poset sequential Monte Carlo is just a recommendation of how to choose Tj and and the approximations to the density that you're interested in a way to make the weights to be approximately the same. So Poset sequential Monte Carlo was originally devised in this paper from Bochard-Coté from 2012. And the idea is that you have some kind of combinatorial object. So let's say trees. And you're going to, instead of directly sampling from the space of trees, you're going to build successive partitions or refinements of the space of trees, right? So you can think about, for example, in the first coordinate I'm going to sample from, there's only the root of the tree, somehow. So everybody starts at the same point. And the root of tree is nothing less than a partition that has all of the trees, right? Sorry, that's not the right way of thinking about it. It's a tree in which each one of the languages is its own forest, is its own tree. So you have simply a partition in which each one of the nodes of the tree is its own tree. Then for the next level of the tree, you can think about you choose two arbitrary nodes and you join them, right? And then, so what you get is, instead of you having D trees, you have D minus 1 trees, in which one of these trees has length 2 and the other trees has length 1. And then you can successfully look at these refinements until in the last coordinate you just have all of the trees. But you can think about this in more generality. So let's say that you have this sample space theta here. And then I'm going to just define some arbitrary, some other arbitrary sets, theta 2, theta 3, theta 4, theta 5, such that theta 1 is just a unitary set here. And then I'll define this G function that just maps every element from the last coordinate to the previous coordinate. So G's GIs, they define partitions over thetas. And the idea, or the trick in Poset sequential Monte Carlo, is that I'm going to choose epsilons such that I only move inside the partitions that are induced by these functions. So this picture hopefully makes it easier. So let's say that the parameter space that I'm actually interested in has 5 elements, 1, 2, 3, 4, 5. I'll define this intermediate parameter space that has partitions of the elements of the parameter space. So here I have 1, 2, 3, 4, and 5. And you can think about G2 as just a function that maps 1 and 2 to the same element, 3 and 4 to the same element, and 5 to the single element here. And then in the end, I just map each one of these elements to the coarsest partition, which is a partition that has all of the elements in the sample space. So what am I sampling from? I will initialize all of my particles from this coarsest partition. So all of my particles are going to be 1, 2, 3, 4, 5 in the 4th coordinate. So I'm saying that in the end, I might be in any one of these elements. And then what Poset sequential Monte Carlo says is that, okay, which one of the finer partitions takes you to this coarser partition? All of the finer partitions can take you there. So you just take a proposal that with some distribution gets you here, with some distribution gets you here, and with another probability gets you here. And then you can take your weights and resample once you get to the second coordinate here. And then once you get to these finer coordinates, which is the second element of your vector, then you also take proposals that only get you in a finer element of that coordinate. So let's say that you started, so your initial coordinate was 1, 2, 3, 4, 5, and then you went in your second coordinate to 1 or 2, right? So once you got here, you're going to take a proposal that only takes you to 1 or only takes you to 2. And that's what you're going to do in general. So that's a basic idea of post-set sequential Monte Carlo. You remember that in sequential Monte Carlo, you wanted to simulate from a complicated distribution, and you couldn't quite do that. So you transformed, instead of just sampling from a single random variable, you sampled from a vector of random variables. And then you had to find out where this vector was coming from. Well, here you start from a complicated posterior that you want to sample from. Let's say your posterior is over trees, or in this example, you wanted to sample from 1, 2, 3, 4, 5. And then you just take successive refinements of this sample space that you want to sample from. And then you just take proposals that go in the inverse order of these refinements. That's the basic idea of post-set sequential Monte Carlo. And doing this simplifies a lot the work that you have. So what's going on? Previously, you had this arbitrary Markov transition from the future to the past. But here you can take the Markov transition just to be the indicator that you're inside the refinement, because that's what you're actually sampling from, right? So the Markov transition is just ones or zeros. It's 1 if you're going back through one of these lines, and if 0, if let's say the idea is to go from 3, 4 to 2, then the Markov transition would be 0 because you can't go in the reverse order. So in a sense, the Markov chain disappeared because once you know exactly what theta d is, you know exactly what path it took to get there. And then, since you have t's just being equal to 1, then you have this simpler weight that doesn't have the tj's. It just has the approximation for theta at coordinate j divided by the approximated for theta at coordinate j minus 1 times where the proposals are actually coming from. So how do you actually do these refinements for trees? It's very simple. Let's say that you have clock trees. And let's say uj minus 1 is just one of those elements of the partition that I said. So these are forests, right? In which the modern languages, each one of them are leaves of trees. And you start with a forest that has each one of the modern languages as its own tree. And then at each step, you successfully join these modern languages or these trees into, so you have, let's say, a tree that is modern language 1 and a tree that is modern language 2, and then you can propose to join 1 and 2, and you get a single tree that is a triangle that has language 1 and language 2 as the leaves of this tree, right? So these are the refinements that are being induced in the space of trees if you do these proposals. And then you can join these trees. So after you join the forest of trees successfully, in the end you get to a single tree. That is what the combinatorial object that we're interested in. So the way to simulate from these proposals is very simple. You just take the new tree, the new forest at coordinate j, and you just copy the previous coordinates. Then you pick at random without replacement, you picked two trees from this forest. You remove these trees from this partition that you had before, and you just add a new tree that just merges tree 1 and tree 2 into a single tree. So what's going on here is that in the end, we start with a forest that has D trees, and at each step, we have a forest that has one less tree, until in the end, we have a forest that has a single tree and merge all of the previous trees into a single tree that has all of the modern languages. And in sequential Monte Carlo, in poset sequential Monte Carlo, we had to assume that we were always going back in the space of refinements when we were considering the proposals. And this might be hard to do. And there's an adaptation for it. So this is easy to do for clock trees. So it's trees that we know exactly the order in which the languages merged. But some of the time we don't know the order in which they merged. So we might be interested in non-clock trees. And then it's harder to follow this refinement scheme. But then there's this other type, which is a generalization of poset sequential Monte Carlo, that is combinatorial Monte Carlo. And then you just choose the reverse Markov chain to be a uniform among the points that you can go when you're going back in the proposal. And that will just lead you a combinatorial problem that you have to count how many ways you can move from one refinement to another, right? And it's important for non-clock trees, which are the ones that I'm using here. But I didn't want to talk too much about this combinatorial problem. This is very similar to poset sequential Monte Carlo. And poset sequential Monte Carlo gives a very nice intuition about what's going to happen with trees. So what's going on in the sampler that you're going to build is that it's more or less as some kind of clustering scheme. But it's not an exact type of clustering, right? Because it's not exactly the same as clustering. Because in clustering, we have a single particle. Let's say we start with this forest in which each language is its own tree. And then we successfully join these trees. And then in the end, we have some type of dendrogram. But we have a single dendrogram, right? So that's not what we're interested in a posterior. We want to have a distribution of our trees, right? So in a sense, what sequential Monte Carlo is doing is, instead of doing this clustering in a deterministic way that is greedy, instead of doing that, we are doing it in a random way that is randomness that is trying to approximate the posterior, right? So in each one of these steps, we are going to have, let's say, running the J, we are going to obtain getting the J hierarchical clustering of our languages. But we're going to get lots of these dendrograms, and these dendrograms are going to be approximately distributed according to our posterior that we're interested in, right? So you can think about this as more or less an adaptation of clustering, but to the context in which we want to sample from our posterior for trees. So we have random dendrograms or something like that. And that's why I thought that this trick was useful to understand sequential Monte Carlo, or the type of sequential Monte Carlo that is used to sample from trees. Okay. So for our problem, there are some complications. So for the problem of linguistics, there are some complications. What are these complications? So poset sequential Monte Carlo was developed in the context of phylogenetics mostly, right? And in phylogenetics, for some models of phylogenetics, the tree is your only parameter. And therefore, it's very useful to do poset sequential Monte Carlo in this type of model, in which the tree is your only parameter, and you're getting the posterior for the trees that you're interested in. But for our model, we had our parameter space wasn't just the trees. It was the trees times all of the regular sound changes that happen in that tree. So the level of approximation that poset sequential Monte Carlo is giving us is not enough for us to get our weights to be approximately equal to 1. So, or approximately uniform. So if we wanted the weights to be approximately uniform using just poset sequential Monte Carlo, then we would have to, at some point, let's say we join the nodes, we join different trees, and then we'd have to attach all the regular sound changes that happened at that point with a given distribution. And that would have to be a known distribution from where the proposal is coming from, right? But in general, that's going to be very hard to do, to sample from the regular sound changes in a way that it's close to the posterior. So it's very hard to come up with these approximating posterior distributions for the poset sequential Monte Carlo in this parameter space that is nested in a certain way. So it's trees, and inside the trees, there are sound changes in each one of the nodes. So there's this idea that is, okay, let's try to build a proposal that, let's say, you join different branches of the tree at random, and then you have to come up with regular sound changes for that node. So instead of trying to figure out an analytical proposal for how to join how to come up with the regular sound changes that happen at that node, I'm going to use a sequential Monte Carlo that is going to generate the proposal for the regular sound changes that happened at that node, right? So there's this sequential or this poset sequential Monte Carlo in the outer layer that is taking care of the trees. And then there's a sequential Monte Carlo inside that is generating the proposal. But then you have a problem. Remember that whenever we talked about a proposal, we had to evaluate the density of the proposal that we are sampling from. It always appeared in the denominator of our sample weights. And in sequential Monte Carlo, we are generating an epsilon that comes approximately from the quantity that we are interested in, but it's not exactly the quantity that we are interested in. So what would we use as a sample weight for the outer sequential Monte Carlo if we don't know from where we are generating our proposals? Right, that's the problem. You can take a very complicated sampling scheme to generate your proposal, but and in the end you don't know the density that you're simulating from, and that becomes a problem. So before I go into nested sequential Monte Carlo, I'll talk about the idea of how to do this. So how can you use some sampler that you don't know what density it's sampling from and use it as a proposal inside a method that uses proposal? So typically, a proposal is a quantity that has two functions attached to it. So key is our proposal here. And this was, and what are the functions that are attached to a proposal? First, it has to generate a random number, epsilon, with this function generate. And then for each one of the random numbers that you generated, it's able to evaluate what is the density of the proposal at that point, epsilon. Or maybe not exactly the density of that point, but at least evaluate a quantity that is proportional to the density from where epsilon is coming from. So that's the regular way that you think about a proposal, right? So let's say you have some kind of Markov chain Monte Carlo, and you have a proposal there. At some point, you have to compute, let's say, the Metropolis-Hastings ratio, and then there will appear a quantity that is where the queue in which the proposal is coming from, right? So generally, when you think about a proposal, it needs to have these two quantities attached to it. So for example, MCMC and sequential Monte Carlo also has the proposal in the denominator. So that's the usual way that at least I thought about the proposal. And then there's this paper from NASA from 2015. And he suggests that you don't actually need all of that from a proposal. There's this generalization of what a proposal is. So a proposal, you just need this generate function, and it generates you a pair of random numbers. So it generates you epsilon and c. And then you need epsilon and c to be balanced for the distribution that you wanted to propose from. And balancement is just that the expected value of g of epsilon for every g times c is going to be the average of g of epsilon according to the proposal that you're interested in. Right? So before, if epsilon was a proposal, if epsilon was being generated by a proposal for tilde f of epsilon, then you would have to be able to compute tilde f of epsilon. And what he tells you is that no, in order to use a proposal, you actually don't need tilde f of epsilon. You just need this balanced random variable here. So this balanced pair of random variables, which is epsilon and c. And balanced means that they satisfy this condition. And it's easy to see that if you have the usual proposal, then you can generate this type of proposal that NASF suggests. But this is more general. So there are cases in which you can get this type of proposal, but you cannot get the previous one, right? So why am I saying this? I'm saying this because in the end, we are going to use sequential Monte Carlo as a proposal inside of another sequential Monte Carlo. And what the distribution of what I'm getting from my sequential Monte Carlo, I have no idea of what that is. But I can build sequential Monte Carlo as a proposal in the sense of NASF. So I'll add an extra quantity C, and then it will be balanced for the posterior that I want to sample from. So that's the idea. And this will simplify our computations. So in order to understand this, instead of presenting the theory for nested sequential Monte Carlo, NASF presents just this toy case, which is nested importance sampling. So what he's going to do is he's going to use importance sampling as a proposal inside of another importance sampler, right? So what is he doing? He says, importance sampling can generate a proposal for us. And how does importance sampling generate a proposal? You just construct an importance. So generally, f of epsilon is the goal distribution for your proposal. You want the result of your importance sampling to be balanced for f of epsilon. So instead of generating a sample from f of epsilon, you generate it from some other quantity, f of zeta, let's say. And then you have, in your importance sampling, you have the importance weights, which will be f of epsilon over f of zeta. And then you just sample from all of the zetas that you got in your importance sampling, a single one, but you sample it from the sample weights. Right? So you have a density f of zeta that is just something you're proposing in the inside importance sampler, and you want it to be targeting f of epsilon. So you just generate lots of random variables from f of zeta, compute their sample weights, and then you just resample according to the sample weights. But you would just be sampling from f of epsilon if you had an infinite number of particles, and you don't have that. You have a finite number of particles, right? So your density, the density for the result of your importance sampling, which is just this random quantity epsilon, is not exactly f of epsilon. So epsilon is not coming from the proposal that you're interested in. But instead of trying to adapt that, you will consider another quantity here, C, which is the average of the sample weights in your importance sampler. And then epsilon C is a proposal for f of epsilon that you're interested in, even though each one of these epsilons is not coming from f of epsilon. It's just something that is coming from the importance sampling, this importance sampling scheme that we defined. And then based on this balanced proposal that you have here, he defines another importance sampler that is using this pair epsilon C as a proposal for that importance sampler, and it wants to target some distribution f of theta, right? So you use as your sample weight f of theta. You usually use as a sample weight f of theta over f of epsilon. So if epsilon was coming from f of epsilon, you'd use as your sample weight f of theta over f of epsilon. But in this case, epsilon is not coming from f of epsilon. It's coming from that importance sampler that you used as your proposal. So in order to correct for that, instead of using just f of theta over f of epsilon, you use as your sample weight c times f of theta over f of epsilon, right? And something interesting is that epsilon is not coming from f of epsilon either, right? That's just what you're trying to target when you're using the internal importance sampler. And what he proves is that this, if you use these as the weights in your importance sampler that is outside and using the internal importance sampler as a way to get proposals, then you are targeting this distribution here. C times f of theta times the joint distribution of epsilon and c over your target f of epsilon. And you can get that in a simple way. You can just think about here in your sample weight. You would want to divide by the distribution that epsilon and c are actually coming from. And epsilon and c are actually coming from this joint distribution of epsilon and c. So you just divide by epsilon c here and multiply by epsilon c. And what remains is the numerator that is the target distribution that you're actually sampling from with your importance sampler. So this is the target that you're actually sampling from. And the trick here is that since c and epsilon are balanced for f of epsilon, then once you integrate out, so this is, you can think about it as an importance sampling that is sampling from this joint random variable epsilon and c, right? Once you integrate out c from this target distribution, since it's balanced, the only thing that is going to remain is f of theta. Because the definition of balance is that if you integrate c times f of epsilon c, what's going to remain is f of epsilon, and it will cancel out, and therefore only f of theta is going to remain. So what he showed is that this is just a toy example. The authors don't think that nested importance sample is useful in practice. But it highlights the idea of what nesting is doing for you. You instead of building a proposal that you know what the density is, instead of that, you build some mechanism that generates the proposal for you that you don't know where the density is coming from, but you don't know where the density is coming from, but you know that it is balanced in a certain way for the density that you're interested in. In just being balanced is enough for using it inside of importance sampling. And the generalization of this is nested sequential Monte Carlo. So nested sequential Monte Carlo is just, I'm going to do sequential Monte Carlo inside of another sequential Monte Carlo. So the sequential Monte Carlo that is inside is going to give me the proposals for the sequential Monte Carlos that is outside, and it's the one that I'm actually interested in. And it's not that hard to prove that if you do sequential Monte Carlo inside of sequential Monte Carlo, and you are using the inside sequential Monte Carlo as a balanced proposal in the sense that NICEF defined, then the outside sequential Monte Carlo, or the result that you're going to get, is a particular kind of sequential Monte Carlo that is targeting the distribution that you're interested in. But besides just being a sequential Monte Carlo for that distribution, it has the quantity that you're simulating from as the marginal distribution that you're interested in, but it's simulated in an augmented space, and that's the trick that allows you to simplify the problem, right? So this nested sequential Monte Carlo is a particular type of sequential Monte Carlo, and since sequential Monte Carlo is a particular case of sequential importance resampling, then we prove that it's converging to the right place that we're interested in. But then you have a problem. If you get a proposal from a sequential Monte Carlo, how do you show that it's balanced? And the proof was made. The proof is done from NICEF, but it's based on this beautiful paper from Andrieux I don't know how to pronounce his name, sorry. And this one was presented in, I think, the Journal of the Royal Statistical Society. And he shows that the average weight in a sequential Monte Carlo has some nice properties that can be used to show that the sample is balanced. And something that is very beautiful about this result is that it connects several different methods. So there's another type of sequential Monte Carlo that is called particle, well, it's actually a type of Markov chain Monte Carlo, particle Markov chain Monte Carlo. And it's a type of Markov chain Monte Carlo that uses, as your proposals inside of MCMC, sequential Monte Carlo. And the proof that particle Markov chain Monte Carlo is actually Markov chain Monte Carlo and is sampling from the right distribution is based on Andrieux. And the proof that sequential Monte Carlo inside of sequential Monte Carlo is a particular type of sequential Monte Carlo is also based on this result. So this is a very, very beautiful result. And if you look at the commentaries, everybody that was commenting said it will have lots of, it will spread out in lots of methods in Bayesian statistics. So very interesting result. And what so here's written just what I said before, that you can, that NICEF also proved that this scheme that has sequential Monte Carlo inside of another sequential Monte Carlo is just a particular type of sequential Monte Carlo in an augmented space that is sampling from the right distribution for you. So in the end, you can nest one inside of the other, and even you don't know the density of where your proposals are coming from, in the end, you're sampling from the right distribution. And there's some adaptations of this nested sequential Monte Carlo to the evolutionary model, but they're quite technical, so I didn't want to talk a lot about them. But you can think about as an outer layer of the sampler and an inner layer of the sampler. So here we are going back to, after this interlude for computations, we are going back to the evolutionary model. And in the outer layer, we are using a sequential Monte Carlo that is considering refinements over the tree space. So it's just considering that hierarchical clustering, or that random hierarchical clustering that I was talking about. And the inner layer happens every time I join two trees of our forest. I have to attach regular sound changes that happen in that node of the tree. And I'm going to propose those regular sound changes instead of that's a random matrix, right? That is 50 by 50. And instead of trying to sample from that matrix at random, I'm going to use a sequential Monte Carlo to sample from from this random matrix that is inside of each one of the nodes. And then I'm going to just get this proposal that comes from the sequential Monte Carlo and attach it to the tree that I got in the outer layer, and that's going to be the proposal that I get from my sequential Monte Carlo. And then in this inner layer, of course, there's some extra computational problems that I'm not, remember that I'm only considering as my parameters the regular sound changes that occurred and also the trees. So remember that there was this extra parameter that was the ancient words that we don't know. And since I'm not sampling from those ancient words, this is something that I'm integrating out of the posterior. So I have to find a way to integrate them out and do the computations. And that's just something that is very known in phylogenetics. There's this Felsenstein's peeling algorithm that it is a way of computing these, this integrated out posterior in a way that it does economy in a lot of the calculations, so that you don't have to repeat several of the calculations. But I didn't want to go too much over this. So we could, we built our sampler for the phylogenetical, for the posterior in the phylogenetical model by adapting this nested sequential Monte Carlo. And then here are just some examples of what we found when we ran this. So this, I'm just looking at the sound changes that happen, let's say, from Proto-Germanic to Dutch. And you can see here that you have this S goes to sigma, and this other, these similar sounds. So this is a gamma that goes to G with a high probability. And if you look at Proto-Germanic and what probably happened, these seem more or less, these seem reasonable to linguists. And here you have, for example, what happens from Proto-Indo-European to German, right? So that's the case that I was discussing previously. And it finds, for example, Grimm's law here. Remember that in German, you have that all the P's go to F's. So for example, in Portuguese, you have pai to be father, let's say, and then you have, in English, father, which starts with F. So the model is finding the regular sound changes that happen here. And you also have this S phoneme that is going to the schwa phoneme that is like something like sh, which the linguists also found that was reasonable. And here it's giving very low probability to these sound changes, and these are probably incorrect. But then you could, for example, use a threshold in the posterior probability to filter out these ones that are proposed with very low probability. And here is the mode of the posterior distributions that we found. So they are posterior distributions over trees, and they also have regular sound changes in each one of the nodes, but I removed the regular sound changes from the tree just to show the tree. And it's more or less what a linguist would expect. So here you have Dutch and German have a common ancestor, and then this ancestor goes together with English, forming the Proto-Germanic family. Then here you have French and Italian, and then Portuguese and Spanish. Each one of them goes together and becomes the Romance family. And then the Romance family goes to... This one is a little bit more controversial, that there's this in-between node here. What linguists usually do is they don't construct this in-between node. They just link it up to this last node and just link this one up to this last node. And then you have Armenian, Greek, Proto-Germanic, and Romance as individual families of the Proto-Indo-European family, right? Subfamilies of the Proto-Indo-European family. But all of these families seem to be correct, and the model is suggesting that there might be this subfamily here that has Romance and Proto-Germanic inside of it before you get to Proto-Indo-European. And that's controversial in linguistics. I'm not sure. I didn't talk to a lot of linguists. I talked to a few of them, and it might be reasonable, but something that should be investigated, I guess. And then I ran the model for some other databases. And here there was something strange that happened, that you get the same families that you had before. For example, English and German, you have Proto-Germanic, French and Latin. So this one actually had an ancestor language inside, but it found out that French and Latin go together to Romance family, let's say. But then here, instead of putting Albanian as a separate leaf that goes here, it also added Hawaiian here. And then Hawaiian, this doesn't make sense. It's probably not in Indo-European. But Hawaiian is a very strange language that has a very limited amount of phonemes. And this might be doing some harm to the evolutionary model. So maybe we'd like to put some type of regularization constraints if the language has too few phonemes. But this is something that we're still investigating, what happened here. And then here we have Navajo and Turkish, and they are correctly seen to be outside of the Proto-Indo-European family. So most things seem to be correct. The only thing that is a little bit startling is Hawaiian inside of Proto-Indo-European. And this one is like obviously, well, it's hard to say obviously wrong because everything there's unknown, but most linguists would believe that this is wrong. So I'd have to investigate what assumptions don't make sense and are leading the model to believe that Hawaiian is happening here. But one thing that is at least a little bit relaxing is that if I remove Hawaiian from the database, then the structure of the tree remains the same. So the model is more or less robust. It doesn't depend on this single data point. It's not that Hawaiian is making it insane, and then it's getting everything wrong. It's just that it got Hawaiian wrong, but the rest of the tree without Hawaiian stays the same. So as conclusions, it seems that the model successfully captures regular changes that happened in the languages, but there are lots of improvements that I could do, or people who are interested could do. So instead of just modeling a single phoneme, we were modeling just the initial phoneme for each one of the languages. You could model whole words. But then instead of just using unconditional sound changes that we have here, you'd have to also use conditional sound changes. So conditional sound changes, you say, let's say, P becomes F, but only if the following sound segment is a D, let's say, right? So that's an unconditioned sound change. And we didn't use it, of course, because we had a single phoneme. But then you'd have to use that there. And then instead of having a simple model for the words, you'd have probably a hidden Markov chain inside that you have to do some extra calculations. We could also add to the model borrowings. So we decided that we modeled that the only source of previous words, the only influence in the words of a given descendant were its ancestor words. But we know that that's not the case. For example, so French is not the immediate ancestor of English, but English got several words from French. So we could try to add some kind of aerial model in which, besides the tree being responsible for sending words from the ancestor to the descendant, you could also have words moving in space, let's say. That's something that you could try to do. And another thing that we could use is that both in defining the regular sound changes and in the elicitation of these sound changes, we try to look at each one of these sound segments at a time. But these sound segments, they seem to be structured according to universal rules, right? So remember that there's a topology in which these sound segments are inserted. And in a sense, the linguists believe that if a sound segment goes from here to here, let's say, then you might expect that all of the sound segments that are nasal, so nasal is this manner of articulation, all of them might become plosive, that is here. So there's some correlations in how the sound segments move, and we model it in a way that each sound segment moves independently. So we might want to try to add this correlation to the model and take into account this latent features that exist in the minds of linguists, but we are only taking them into account through the prior elicitation. So we might try to put into our model this latent space of features that the linguists use. So these are just some ideas of how to generalize the model. And I guess that's it for today. Thank you.